Speaker.
Good afternoon. In the true spirit of the Jones seminar, I'm going to start by explicitly considering the relation between science, technology, and policy, and science, technology, and society. As scientists and engineers, most of us like to think that we have a direct channel to the decision makers and elected officials of society. This is especially true as our world's problems become more complex and more technical. However, in reality, this connection isn't as clear as we may think. In part, the strong signals we're sending are diminished or weakened because of our own disclaimers regarding uncertainty and the need for future research. Additionally, we need to remember that we're sharing bandwidth with the public, whose own preferences and beliefs they'd like to have heard by decision makers and politicians. These typically involve issues regarding economics, ethics, and risk, much more so than technical and scientific issues. Therefore, the question I'd like to address today is, how can we account for society's beliefs and preferences in the models that we use for supporting decisions? And in my own research, I address this question in the particular context of natural resources, environmental health, climate change, and energy policy. Now, I'm especially interested in the relations between preferences and formal models as opposed to other ways of representing knowledge, because models are essential for understanding and predicting the behavior of complex systems. Models integrate the knowledge of different disciplines into a single framework that can be used for generating predictions about outcomes of our decision options. Now, it's important to remember that our models aren't crystal balls. They have uncertainty associated with them, but they can be used to explore the implications of a variety of assumptions and scenarios. I'd like to give the example of, in this plot, which is coming from the Intergovernmental Panel on Climate Change. It's showing projections of future temperature change relative to pre-industrial times, or relative to a baseline, I should say, of 1990 levels. And what you can see when this is temperature change along this axis, and year projecting forward into 2100 along this axis. What you can see is, for the different lines, these represent different scenarios, different socioeconomic and technical developments moving forward. And you can see the vast diversity in the projections associated with each of these. And each of these, we don't know which might actually unfold moving into the future. Furthermore, you see for any given model, or any given scenario, there's a wide spread or associated with the uncertainty in model-based forecasts of temperature, even conditional upon that socioeconomic development. What that results in is the dark shaded area, which is a kind of envelope across all the a model ensemble, that is a kind of model average across the variety of different socioeconomic scenarios. The lighter shaded area then represents the individual predictions of any given model for any given scenario, which is even broader. And you can see just the tremendous uncertainty and ambiguity associated with trying to predict the future with regard to temperature change. It's no wonder that policymakers perceive a mismatch between these kinds of uncertain model forecasts and their desire for definitive guidance regarding their decisions and policy choices. And it may be this disconnect that explains the lack of action on an international level regarding climate change. Now, this reluctance of policymakers to engage in climate change, given the uncertainty, is in marked contrast to the preferences of the public. These are survey results conducted by Yale just a couple of years ago regarding and it's intended to be a nationally representative sample, regarding the support for the public for a number of activities that are intended to reduce the effects of climate change, reduce the effects of increasing temperature. Things such as supporting renewable energy research, providing tax rebates for efficient cars and solar panels, regulating CO2 directly, asking utilities or requiring utilities to produce 20% clean energy, and signing an international treaty to cut emissions. You can see the majority, in all cases, of respondents support these policies. And this holds across all countries. In fact, the majority of the population in most developed and developing countries shares the concerns of scientists regarding the impacts of climate change on the future well-being of humanity and biodiversity. So there's a kind of conundrum here. There's a mismatch between people's personal preferences and perception of risk and the ability of democratic societies to implement specific political actions in response to scientific risk assessments. And so this is the kind of call to action that my research group has taken to try to work on addressing new methods to identify strategies that can succeed, both technically and politically. Our research group is addressing this need by developing models and modeling tools that incorporate society's beliefs and preferences for economic welfare, time, and risk, and the behavioral and decision-making implications of these preferences. That is, how do these preferences play out in the real world and the kinds of decisions and the behavior that people undertake. Now, this is a challenging task. One key challenge is how do you characterize the preferences and the behavior of so many diverse stakeholders regarding an issue like climate change or other environmental and natural resource management problems. Another challenge is how do you accurately represent not only these individual preferences, but the complex interactions that occur between them, between issues of economic welfare, time, risk perceptions, and risk and beliefs about risk. So what I would like to do to kind of demonstrate these challenges is give an example of how something called decision theory, which I'll be talking more about, can enable action in the face of complexity. And the example that I want to give is something that's I know you all place quite a bit of importance on. That's Jones Seminar cookies. Roger, who typically, I don't see him. Roger, are you back there? Roger typically keeps an eye on the cookies in the back, and he says recently he's noticed people taking 2, 3, as many as 4 or 5 cookies. And this has started to become a concern. As the student population grows and as the dean expects, the Thayer school may double. And so cookies may actually become an increasing burden as a line item in the overall school budget. You all know Larry McKinnon has gotten a lot of attention or appreciation among us for maintaining a balanced budget at 20 years straight. And he's had to do this by making some hard decisions. So imagine that the dean has decided to cut cookie consumption and ration cookies at a rate of an average of 1 cookie per week. And, but to do this, to begin this and to kind of eliminate the burden on all of you, or to reduce the burden on all of you cookie lovers out there, he's going to give you some choice. We're going to try a pilot program in which he gives you some choice in the way in which your own cookies are allocated. So you have options. One option is you get a cookie a week, the kind of standard idea of consuming 1 cookie per week, and that's your ration. You could also take the option in which you front load your cookie consumption. You take 2 cookies in the first week at the cost of not having any cookies in this last week. Or you could reverse this. You could hold off on your cookie consumption until the last, so postponing your first cookie and so that you can enjoy 2 at the end. Or, out of the kindness of his heart, Joe has agreed to stand in the back of the room, and when anybody comes in to get their cookies, you can have the choice, and he'll flip a coin. If you get heads, he'll give you 2 cookies. If you get tails, you won't get any. I'm glad Joe's not here today. So let's label these A, B, C, and D. So which would you prefer? How many would prefer A? The steady cookie consumption. This is a serious choice, so give this some thought. All right, how many would prefer B? Oops, sorry. How many would prefer B? Yeah, B. You want a couple? Yeah. How many would prefer C? Okay, interesting. How many would prefer D? All right, we got some gamblers here. Nice, all right. All right, so what I'd like to do is walk through some of the considerations you may have made in choosing your cookies and use that as a way to demonstrate some of the basic principles of decision theory. So one important notion is the notion of diminishing marginal satisfaction. That is, when you considered the choices between A and B, you had to consider whether the joy of having 2 cookies next week was worth the pain of not having any cookies in 3 weeks' time. And this can be represented by basically that comes down to thinking, is 2 cookies worth twice as much as 1 cookie? Is 3 cookies worth 3 times as much as 1 cookie? For most of us, that's not the case. Most of us, we reach this kind of satiation or saturation point regarding cookies and many other things in which we consume or enjoy. This can be represented by a so-called concave utility function, the red line on this plot here. And this is a particular functional form that's popularly used to represent a concave utility function. It's as they say, it's concave, and it's a function of 1 parameter, gamma. And this gamma is referred to as elasticity of marginal utility. That might be a complicated sounding term, but it basically means how much more satisfaction do you get by each additional cookie you eat. Okay, and does that increase or decrease, and how strongly does it increase, or in this case decrease, the more cookies you consume? And with increasing values of gamma, this curve becomes more concave, meaning that you satiate earlier in your cookie consumption. Okay, the other choice you had was between A and D. And this is a risky choice. You may not end up with any cookies, and essentially you have to decide whether the attraction of having the joy of 2 cookies is worth the risk of not having any. Now, interestingly, the same concave function can represent your attitude towards risk. Most of us are averse to risk. Many of you chose option D, meaning you're attracted to risk. That may or may not actually be the case if you consider that more in longer-term life decisions. But most of us are averse to risk. Yeah. Most of us are averse to risk. And let me kind of walk through why this concave utility function represents risk aversion. You have the choice between no cookies and 2 cookies, or you have a gamble between no cookies and 2 cookies, and it was implicitly a 50-50 gamble. I presented it as a coin flip, which most of us take to be a 50-50 wager. And so if we think about the utility, where this is utility, of those 2 possible choices, no cookies or 2 cookies, we can plug them into this function, and we get the utility on this axis. Now, if we take the average of those 2, weighted by their associated probabilities, that's called the expected utility, and that's what this is. This is just a sum of probability-weighted utilities. Now, that's the expected utility here. Now, if we plug that back into the utility function and figure how many cookies is that worth, that's called the certainty equivalent number of cookies. In other words, that's the cookies that give us the same level of satisfaction for certain, when we have that for certain, as this gamble does under conditions of uncertainty. And the difference between the expected number of cookies, again, the average numbers of cookies we could expect to get in any given week would be 1, the average of 0 and 2. The difference between this certainty equivalent number of cookies and 1 cookie is referred to as the risk premium. It's essentially the amount that we're willing to give up in order to avoid a condition of uncertainty. So if we're risk averse, we have a positive risk premium, we're willing to give up something, a quarter cookie in this case, in order to avoid the risk of not having any cookies. Now, we can go back and use the same utility function I described earlier. So the expected utility is really just a probability-weighted average of this functional. And now this gamma represents strength of risk aversion in addition to elasticity of marginal utility. And with increasing values of gamma, we see stronger risk aversion, meaning that the risk premium becomes greater. Okay, one more option you had here was between B and C. And you had to decide whether you wanted your day in which you get 2 cookies to be sooner rather than later. For most of us, things we like, we'd rather get sooner, and things we don't like, we'd rather put off further. It's the difference between impatience and procrastination. We represent this notion of impatience, which most of us are. Many of you would prefer to have the 2 cookies sooner rather than later, by discount rate. It's a time discount component that basically says things in the future are worth less to us now than things we get sooner. So for example, a cookie we would receive in about 2 months at a discount rate of 10% would only be worth about half a cookie today. A cookie we have to wait a year for at a time discount rate of 10% is only worth a few crumbs. So you see, even something that apparently sounds small, like 10%, really has a dramatic difference in terms of how we value future satisfaction. Okay, so putting it all together, this is, I recognize this may be a complicated expression, but it's basically the component has 3 components to it. It has this notion of marginal satisfaction that I described by the concave utility function. It has a component of risk aversion, the probability-weighted sum of these utilities. And it has a component of time discounting, dividing by 1 plus the discount rate raised to the numbers of time periods. And so this leads to a present value expected utility. Right? So it has those components: present value, time, expected regarding expectations over risk, and utility to address the idea of diminishing marginal utility. And so among our cookie choices, we would want to choose the one, if we were being a rational cookie decision maker, we would want to choose the cookie time series that maximizes our present value expected utility. And so for most of us, being risk averse generally, preferring more to later, or another way to think about that is that we prefer to smooth our consumption. We don't prefer to have periods in which we have little, and this is related to the original notion of a concave utility function. So if we don't want to wait, so we don't like the situation, we generally avoid risk, and we'd rather not have the situation of no cookies rather than 2, because these have diminishing marginal utility. Most of us would prefer A. It seemed like among the hands I got that was a popular choice. Okay, now how does this all relate back to climate change? Well, carbon dioxide emissions and the resulting climate change have a risk. They have a risk of reducing future well-being. In the same way, our cookie gamble had the risk of reducing our own future well-being if we weren't successful in Joe's coin flip. Here's a little kind of cartoon regarding how scientists generally perceive climate change, regarding the impacts on society. The red line represents damage costs. These would say that as climate changes and continues to change, we continue to face damages in the form of flooding, loss of ecosystem services, loss of biodiversity, and so forth. And so these are generally expected, with temperature rise, as I showed you in the last plot, to grow something like exponentially. Now, there's costs of attempting to abate those emissions. I should say, I had meant to include a list. These are some of the various costs associated with climate change. I mentioned some of them. Impacts on human health, among those loss of life and property associated with severe weather events, loss of biodiversity, desertification, and so forth. Now, there's an additional cost if we attempt to either adapt or avoid or abate CO2 emissions in an attempt to bring down these damage costs. That's represented by the blue line here. And in this particular scenario I'm showing, might be a kind of business as usual scenario where we don't take particular action or incur particularly high costs to reduce damages. Now, decisions involving how much to reduce CO2 emissions involve difficult trade-offs. Here's a situation where we don't do much that I just showed, a kind of gradual emissions reduction because of low levels of abatement. So we have low abatement costs and increasing future damages. Whereas if we aggressively reduce emissions, we have very high abatement costs in the near term and only moderate or low future damages. And so it's essentially this kind of trade-off. Would we rather pay more now to avoid future damages, or would we rather not have to deal with the problem and put it off for the future? And you can see why this relates to these issues of time discounting, of risk, and diminishing marginal utility. We expect that generations in the future will be better off than we are today. That's been the historical trend. And so maybe they'd be better able to address those damages, not only technically, but financially as well. Now, in reality, there's uncertainty associated with all this. And I'm superimposing now some shaded areas, just as a kind of cartoon representing the uncertainty in damages. It's at least this great. You saw the uncertainty just in temperature alone, let alone the transition to damages, was quite high. And there's also uncertainties associated with abatement costs. And so it's important to add components of risk to these. And the figure on the left has a situation of high risk, a potential, and perhaps a diminishing, but a potential of very dramatically high costs. Whereas the situation on the right has only moderate risk, that the costs are unlikely to exceed a certain moderate amount. And this role of risk in climate decision making has largely been overlooked, both in a public and political sense, but also in a technical sense regarding modeling. And so our goals with the project that I'll be describing now are basically threefold. First, to construct a fully probabilistic model of climate change that accounts for most of the key uncertainties, scientific uncertainties. To then determine the values of rho and gamma, the time discount factor, and gamma being the elasticity of marginal utility and also representing risk aversion, that truly are consistent with society's preferences. So that then we can use these principles of decision theory to assess the implications for policy choice, that is, for a choice of CO2 reduction levels and the timing of those levels. And we have the expectation that with high levels of uncertainty, the risk reduction value, that is, the additional value associated with emissions, that's associated with bringing down risk that comes from emissions reductions, could be quite high. Another way to think about this is the insurance value, that is, the amount we might be willing to pay to bring down the risks of high future damages. So model construction, this is the first step. And as I emphasize, there's uncertainty in every aspect of climate modeling, from the transition of emissions to temperature, well, first of all, from the associated with the basic inputs to models regarding population growth, economic growth, and emission scenarios, through to the representation of these submodels. And typically an integrated assessment model of climate change represents three components: the energy system, that is a technical development of how we produce and use energy; the geophysical system, that is how the climate responds to the emissions coming from the energy system; and the economic system, both because of the feedbacks with the energy system and geophysical system, but also because of those explicit abatement and climate damages that I showed you on the last slide. Now, these submodels then lead to a measure of the output And most models, including the one I'll be describing, take as their output future economic consumption per capita. What this is essentially GDP, but after taxes and after savings, such that it's the amount that we as individuals have available to spend. And while it's not a perfect measure of human welfare, it's a kind of easy metric, and we assume that having economic freedom gives us some degree of flexibility. And so because it accounts for ecosystem damages and such, it's a reasonably holistic measure in this case. So that's our metric rather than cookies in this model. Okay, so in our model, there's uncertainty all along the chain, and we addressed uncertainty in 7 key parameters associated with each of these pieces. And the first set, we considered uncertainty in population growth rate and uncertainty in total factor productivity, which is the key driver behind economic growth and emissions. We considered uncertainty in the future change in carbon intensity, that is carbon emissions per unit GDP, per dollar GDP. Also, climate sensitivity, that is the long-term temperature change associated with a doubling in CO2 emissions. It's a kind of measure of how sensitive the climate is on this, gauged by this metric of temperature exclusively, to increases in carbon dioxide emissions. Carbon cycle mass transfer, that is how is carbon transferred between various compartments around the globe, between the ocean, land, and atmosphere compartments. And then on the economic side of things, how climate damages are translated into damages, and also how expensive are the costs associated with abatement. So here's our model forecast coming from this, and this is a paper that was published in 2010 in Energy Policy. And I'm showing predictions as well as the uncertainty associated with those. And the uncertainty is large, and that's not unusual. It's no larger than any other model, but we're explicit about representing it and including, in reality, the many different components of uncertainty that there are. I'm showing the results here for a so-called business as usual scenario, and the line represents the median, and the shading represents a 90% predictive interval. And so here are greenhouse gas emissions. You can see even in a business as usual scenario where they're expected to plateau because of improvements in energy technology and the rise in cost of fuel as we continue to use carbon or fossil fuel-based resources. But there's dramatic uncertainty. On the high end, if we don't come up with that kind of technology or continue to discover and use new resources, or it could be even lower. Temperature, again, is quite uncertain, as I already talked about in a previous slide, and these results are consistent with that. And then damages resulting from this temperature and other impacts also grow and have vast uncertainty associated with them. And so when these damages together with abatement costs, well, in this case, not much in the way of abatement costs, are translated into consumption, you could see the vast diversity here. We could either expect long-term future growth or even a decline in consumption per capita. And our next challenge is then how can we expect to take results like this and pass those on to decision makers and expect them to make decisions? I already mentioned the value in thinking about present value expected utility, and so that's our next challenge, in taking a measure like this together with the uncertainty and converting it to present value utility, accounting for these aspects of economic welfare, or diminishing marginal returns, risk attitude, and time discounting. Just to remind you, these first two are represented by gamma. You'll see gamma on the following slides, and I want to make sure you remember what that means. And rho, which represents the time discounting. Now, there's a few different approaches to how you might specify these parameters that have been discussed and put forward in the literature and in the policy setting. One of the first efforts to be explicit about thinking about these particular parameters was put forth by William Klein at the Center for Global Development in his book in 1992, The Economics of Global Warming. He adopted a utility function that ignored uncertainty, so it basically was just looking at the present value utility for the purposes of simplification because the extent of uncertainties wasn't fully appreciated at that time. And so then therefore gamma, in this expression that I showed you earlier, but without the risk term, this equation, I should say, represents this notion of economic welfare, where gamma represents the elasticity of marginal utility, and it represents time discounting with rho. And now CT, instead of cookies, is economic consumption in time t, so having a time series of economic consumption. Now, he suggested, based on ethical principles, that the discount rate should be 0, that we shouldn't discount the future, we shouldn't put the future generations' interests, we shouldn't hold those below ours, and therefore we should use a 0 discount rate. even though that may not be how we actually make decisions, it seems to be consistent with this moral principle of protecting the future generations' interests. And then he chose a value of gamma, which is kind of a moderate value, of 1.5. The result is a conclusion, then, from his modeling efforts together with this kind of utility function that supports dramatic or aggressive emissions reduction, again, characterized by this kind of cartoon, where we have high and prolonged abatement costs with the intent of bringing down damage costs. In fact, his conclusion was that we should aim for something like a 75% reduction relative to business as usual in our emissions by 2050. This is what's come to be known as the normative or prescriptive approach to parameter specification. That is, what should we do as a society based upon ethical principles? And how should we behave? How should we translate that into these kinds of parameters? And what does that mean in terms of our actions? Another possible approach is an empirical approach, and this has been put forward by, or argued for by Nordhaus, initially around the same time in 1994 in his book Managing the Global Commons. The empirical approach says we should learn from how people actually make decisions and incorporate what we learn from that and take that to extend that or extrapolate that into how we should be making decisions into the future. Because if people have been making decisions in the way that they have, that seems to imply something about their preferences, and we should then apply those preferences when we think about future behavior or how we value future outcomes. So Nordhaus adopted, in trying to generate empirically based parameters, adopted an economic principle referred to as Ramsey's rule. Ramsey's rule says that the rate of return that a rational investor should expect on any investment should be approximately equal to the discount rate to make up approximately equal to the discount rate to make up for impatience, plus the product of the average consumption growth rate, that is how much does consumption grow from one year to the next on average, times the elasticity of marginal utility. This is referred to as the wealth effect because it basically says that as we become wealthier in the future because of positive average consumption growth, the value of any investment is, or the value of any dollar is less to us because of this notion of diminishing marginal utility. And so this expression relates our average rate of return on investment to rho and gamma, which we're interested in, and g, the average consumption growth rate. Historically, average return on investments has been on the order of 5.5%, and the average growth in consumption has been on the order of 2%. And so these provide some limitations on the values of rho and gamma. It's one equation and with two unknowns, so it doesn't specify these precisely, but it constrains them. And Nordhaus chose a value of gamma of 2 and a rho value then of 1.5 to conform with this. He's changed his views a bit over the years, but this is what he's finally settled on. Now, the implications of these choices as opposed to these, numerically, you may not look like much, but they have dramatic implications for what seems to be socially optimal emissions policy. This suggests a very weak or gradual emissions reduction, something on the order of 25% or less by 2050, characterized by this kind of cartoon where we don't spend much on abatement and we face the risk of long-term damages. And that's largely because the discount rate is significantly higher than it is here, while gamma isn't dramatically different. Now, both of those views ignored uncertainty. And in that empirical approach, Ramsey's equation only holds under conditions of perfect foresight. And so it assumes a kind of deterministic view towards the future where we know the outcome. And we just need to consider our choices in the, conditional on that certain knowledge. As I emphasized, there's uncertainty at all levels of climate modeling, and that should be an important part of our choices. And so we really do need to consider present value expected utility, not just present value utility. And this gamma then should represent both the effects of diminishing marginal returns on economic welfare and risk attitude. So what might a probabilistic approach tell us? In other words, what if we could add to this grid a dimension, in addition to empirical and normative parameter specification, add a dimension in this grid which is probabilistic relative to, say, the deterministic approach to uncertainty that I just described? Well, many of you may have heard of the Stern report in 2007 coming out of the British Treasury. One of the reasons it got quite a bit of attention was that it was the first kind of full-fledged attempt to address issues of uncertainty in climate decision making. And this was put forward, the leader on this effort was Nicholas Stern, and he adopted this normative approach, saying that under uncertainty, we should adopt a gamma value of 1 and a low discount rate of about 0.1%, something like the 0% that Klein had suggested, but acknowledging there might be some potential for future discounting, largely based upon individual death rate, which was an interesting rationale for 0.1%. But then a value of gamma, again, a low value relative to these. Now, the conclusion here is also like Klein's was in the combination of normative and deterministic approaches, was that we should have aggressive emissions reduction. Again, something like 75% reduction relative to business as usual by 2050. But the difference being is that Stern and the group involved in the Stern review explicitly accounted for uncertainty, and therefore we have this probabilistic approach. So it seems now there's a kind of dichotomy across this grid between empirical and normative approaches, where normative approaches based on ethical principles and coming up with the parameters say we should take aggressive action. Whereas empirical approaches, based on how people actually make decisions, suggest that we shouldn't do much. We should move gradually. And this has important implications for regulation, the difference between these two. It's not just an academic exercise, and I want to emphasize that point. It turns out that there's something called Executive Order 12866, which mandates that agencies are required to perform cost-benefit assessment of proposed regulations. Many regulations affect CO2 emissions. And so it becomes a question, what benefit should be assigned to each ton of CO2 reduced? For example, if we're looking at fuel efficiency standards, what's the benefit to society of each ton of CO2 that's eliminated as a result of that fuel efficiency standard? How do we assign a number to that, given the kinds of uncertainty that I showed on the last slide? Well, agencies have been at a loss for how to do that. And so the Office of Management and Budget convened an interagency working group to basically say, let's try to settle this issue by coming up with a unified agreement on what's referred to as the social cost of carbon. That's the cost to society of carbon, of each ton of carbon dioxide released. And let's use the best available models to do that. And it turns out that two of the best available models were the model used by Stern and company in the Stern report, called the Page model, and the model developed by Nordhaus called the DICE model. And there was a third model also being used, and it was this collection of 3 models that was used to assess the social cost of carbon. Now, they did so, and I'll give you the results in a minute, but I just want to emphasize that this group, the conclusions of this group have a tremendous influence already on regulations and how we value regulations. Basically, this executive order says that we have to consider costs and benefits, and the magnitude of the benefits of many of these kinds of regulations, like average fuel economy standards, air toxics releases, which have co-benefits associated with carbon dioxide release, new source performance standards on power plants. In addition to thinking about toxics, like I said, these have impacts on carbon dioxide. And so the relative benefits of these compared to their costs is dramatically affected by the value of the social cost of carbon. Also, the social cost of carbon determination provides a kind of first point of reference for how you determine a carbon tax. There's an argument that could be made that if we're going to have a carbon tax, that should be valued at the social cost of carbon. That's one view. And so it's clearly essential what that is. So what social costs of carbon come from these models? I mentioned the 2 of the models that were used were this model DICE and this model PAGE. Well, DICE, with these specifications, consistent with its notion, the outcome that we should only take a gradual approach to reduction, has a high end of the social cost of carbon, its own high end, I should say, of about $50 per ton CO2. On the other hand, the normative approach, which tends to suggest stronger emissions reductions, has double that value, dramatically different, $100 per ton of CO2. Now, what value did the interagency working group adopt? $22. They used something like, although they weren't as explicit about it, something like a gamma of 1 and a rho of 1. And so a low value on the costs associated with carbon emissions relative to these. So clearly there's some room for debate. And this puts emphasis on the need to look at the intersection between empirical and probabilistic approaches. And this has largely been overlooked, and that's been our task. So now, empirical probabilistic approaches, that means under situations of risk, what do people actually do? Well, some surveys have been conducted, and while these aren't perfect measures of what people actually do, they do reveal their intents. One survey of the US population regarding the people's personal financial considerations led to values of gamma greater than 3.75. Now, they weren't asking people for their value of gamma. That's not something people have in their heads. But they were asking them about hypothetical choices. And from those choices, you could back calculate their equivalent value of gamma. Similarly, and maybe more relevantly, a global survey across a large number of countries evaluated people's views towards the economic impacts of national policy measures. And there, too, high values of gamma were supported, on the order of 3 or even greater. I want to remind you, back at this kind of cartoon on when we looked at risk attitudes in the utility function, higher values of gamma mean a more concave utility function, and therefore a higher risk premium, a higher value placed on risk reduction. So how can we learn? The social surveys like that aren't perfect, as I say. They're hypothetical choices, they're not real choices. How can we actually learn how people make decisions? Well, one convenient metric and source of data are investment returns. Investments are inherently risky, and we could look at what kind of choices people make in the marketplace and what kinds of returns do they expect in that marketplace, and see if we can infer parameter values from that. That's something similar to the approach that was taken by Nordhaus with his view of, the constraint in his case of people having perfect foresight. And that was the deterministic Ramsey's rule that I showed earlier. This is actually the deterministic Ramsey's rule. It's not the form I showed you. The form I showed you was this kind of simplification or approximation to it. This is showing the return on investment. This is the rate of return. And you can derive this approximation from this. And as I mentioned before, this essentially represents a relation between the market interest rate and the discount rate and the average consumption growth rate, where the average consumption and growth rate is influenced by the elasticity of marginal utility. Now, for a deterministic or probabilistic Ramsey's rule, there exists, one can derive a probabilistic Ramsey's rule. And when you do that, you find that under conditions of uncertainty, a rational investor should expect a rate of return on a risky investment which is equal to the average rate of return on, or the average return, not rate of return. The average return on a risky investment can be equated to the average return on a safe investment plus a risk premium. And this risk premium essentially represents the uncertainty that investing in this risky investment imposes on this person's future economic welfare, accounting for their risk aversion. And here's the expression for this. This is essentially a first-order Euler equation that's derived from a stochastic dynamic model of investing. But this is this optimal condition under which one can extract or one can relate this average return on investment, the expected return on some kind of risky investment, to a term representing the average return on a safe investment. You see this term looks like this situation, so a condition of certainty, a safe investment. But now consumption growth in this model is also taken to be uncertain. We don't know exactly how much consumption will grow into the future, and so this represents a distribution, and therefore this is an expected value of this term. And then adjusted by a risk premium, which is a covariance term. It essentially accounts for the fact that there might be some relation between an investor's, a particular investment and consumption growth. And if it turns out that if that covariance rate is positive, you don't see that here, but if the covariance between R and G is positive, because this is 1 over G, you have a negative sign out in front. But if this covariance is positive, it turns out that that's a riskier investment, because in conditions where consumption declines, your investment will also decline. Whereas if this covariance is near 0 or even positive, then this term is 0 or even positive, then it's a kind of precautionary investment, meaning it behaves in a way that's counter to the the trends of the changes in consumption growth. So now, given this expression and data on any two investments that have differing levels of risk, we can determine socially relevant values of gamma and rho that truly represent how people have behaved on the market. So we've done this. We've collected data on investment returns and consumption growth and the uncertainty associated with those. And we used what's called a Bayesian hierarchical approach to perform this parameter inference. Bayesian hierarchical models and inference processes add power because they allow you to essentially use the data of all different components simultaneously while still allowing for some individuality in those components. In this case, the components were different nations, and the Bayesian hierarchical approach improved our ability to estimate parameters across those nations. So we collected data from, turns out data were available on 24 nations for the various data that we needed, and inferred values of gamma and rho from that using this hierarchical approach. As I mentioned, these are the parameter distributions of parameter values for individual nations. These are the data that we have from which we can infer these, but then we assume these all come from a common global distribution. They're not precisely equal to that, but they're distributed according to some global distribution, which allows for some variability in nation-to-nation behavior, yet assumes commonality in the basic functioning of the economy and investment returns. Now, in any kind of Bayesian modeling, probability distributions are used to represent the uncertainty in values, in estimation of these parameter values. So the end result is, then the takeaway from the Bayesian approach is that each nation has its own distribution, but some commonality is assumed among them. And this reveals a kind of compromise between nation-specific values and globally common values. So here are just a table of the data from some of the countries that we have. And we used bills as one form of investment that's relatively safe, stocks as another form. You see stocks being riskier, have generally higher average returns. And here's the risk premium, the difference between those two. And you see those that can be quite large. And so we use this Bayesian hierarchical method together with this Euler condition on this generalized Ramsey's rule to infer value distributions on the value of gamma. I'm showing this as a bean plot. This shows the estimated value together with the uncertainty, gamma on the vertical axis, across the different countries. Now, I don't have 24 countries here. I'm showing a subset of the countries from which we had data. And you can see, although there's quite a bit of variability from country to country, you see across the board values that are consistently greater than 2 with an average of about 5.6. And when you use 5.6 in this first order condition, you get a value of rho of 1.5, conveniently the same as a value estimated by Nordhaus. And when you use this model then to evaluate the risk premium that I showed you on the last table, it seems to provide a kind of reasonable explanation. There's a nice fit between the observed risk premium and this model predicted risk premium. And this risk premium, the extent of the difference between these two, has been a kind of conundrum in finance for a long time that people have sought explanations for. Now, I'm not saying this is the right explanation, but it's at least consistent with the magnitude and importantly, the variability in this risk premium across nations. And this was, a graduate student, Pong Ding, was the first author on this study, which was recently published in Risk Analysis. Okay, so coming back to climate change. So what does this actually mean for this cell? I said we've got values, we've estimated values of gamma of 5.6 and rho of 1.5. So what are the implications of this kind of strong risk aversion for emissions reduction? Well, remember, we're calculating a present value expected utility. We've got these parameters. Now, I want to emphasize that these parameters are not just used for post hoc processing of model results. They're actually used by the model actors. We're assuming that the decision makers in the model operate under these parameters. This adds significant complexity computationally to the model, and because of the strong risk aversion relative to other models, requires a large number of model runs. I just wanted to point that out, that it's more than just post hoc processing of model results, but really a fundamental change in the decision-making processes. So what are the implications here? Well, with a gamma of 2, this is showing the relative utility as a function of emissions reduction. And with a gamma of 2, the peak utility is at a value of about 20. This was, gamma 2 was this kind of reference value that other modelers had used. Under our apparently empirically supported value of 5.6, we see a utility that peaks at a value closer to about 50%. with a much greater risk, that is a much greater potential, I should say, not risk in this case strictly, but greater potential at low levels of emission to have low utility, while at low levels of emission reduction, while at high levels of emission reduction on the order of 60 or more, utility doesn't drop off, meaning that the potential associated, we're worse off not doing enough than doing too much, according to this function. And when we explore this a little bit further, you can see that this shape of this curve is a reflection of our model predicted probability of catastrophes as a function of these emission reductions levels, such that and we define catastrophe as a decline in economic consumption of on the order of 25% or more, which has been seen in the past simply from economic fluctuations and recessions and depressions, but might also be a result of dramatic climate change. And you see, if we don't do enough, there's a greater probability of catastrophe than if we start to reduce emissions. And it seems like this is the driver associated with the shape of this curve. In other words, strong risk aversion, like we see with a value of 5.6, puts greater weight on the protection against these kind of severe outcomes, as opposed to just thinking about kind of the expected behavior of the system. Okay, so as a kind of summary, preferences of time, marginal utility, and risk are all essential considerations when evaluating CO2 emissions. And there's empirical evidence that society is significantly more risk averse than typically assumed. This increases the reduction value of emissions abatement and implies then that the risk of economic catastrophe implies a strong preference for at least a moderate level of emissions reductions on the order of 50% by the year 2050. So now this raises the next question that our group is attempting to address. How do we actually achieve this? Given that we want to aim for a 50% emissions reduction, what's the most effective way to do this? The kind of global theoretic model that I just described can inform the level and timing of these emissions reductions, but doesn't actually tell us how such targets can be achieved. These models implicitly assume an omnipotent, rational decision maker, a kind of beneficent global central planner, and we all know that that's, observing Congress recently, we all know that that's not in reality the case. In reality, the world is made up of heterogeneous, boundedly rational individuals who act largely in their own interests. Again, taking Congress as an example. So therefore, another line of work in our group is to develop an agent-based model that it works to determine the implications of the real-world behavior and constraints on CO2 emissions and climate change. I won't have time to talk much about this model, but I'd like to give you a brief overview of its operations and results. This is a schematic of an agent-based model. An agent-based model represents actors by individual decision rules and interactions. Our model as a whole is a model of an economy based upon those individual agents or actors. And this model economy represents the linked dynamics between economic growth, energy technology development, and carbon emissions. And some of the key components of it are heterogeneous actor behavior, something different than the homogeneous rational decision maker of these kind of larger scale models or decision theoretic models. The constraints are imposed on the choices and interactions available to actors, and they act under boundedly rational decision rules, recognizing that they're not omnipotent or omniscient and can't anticipate the future perfectly. Importantly, our model represents the process of technological development through stochastic processes. That is, improvements in labor productivity, energy efficiency, and energy technology are stochastic processes in the model that we can't predict with certainty. And so this is a novel model structure in the climate community that can capture the kinds of details of abatement strategies that can't be addressed by larger scale models, and also assess their robustness to an uncertain future because of the stochastic elements associated with it. I think I'll skip over a description of the agents, other than to mention that there's a few different groups of key agents in the model. There's laborers and consumers, and these consumers in the model purchase and use a generic consumer good, which we call a FNEED. Dr. Seuss fans here at Dartmouth may recognize FNEEDs as being things that all people need, right? And so this is this consumer good that everybody needs and uses to satisfy all their kind of aspects of quality of life. And these FNEEDs require energy and generate emissions in the process. The FNEEDs are produced by consumer goods firms who produce them using machines that are supplied by, or that they buy from capital goods firms. And they combine these with labor and energy to produce these needs. The capital good firms themselves combine labor and energy to produce machines that they're selling to consumer goods firms. And in our model, they function as the hub of R&D activity, this stochastic innovation process regarding labor productivity and energy intensity of their own machines and the needs themselves. We have an energy production firm which buys energy technology from a technology firm and produces and sells energy at a price that accounts for the current market and expected rising fuel costs. And then we have energy technology firms that undertake research and development in three forms of energy related to carbon-heavy fuel sources, carbon-light fuel sources, and carbon-free fuel sources. And with the hopes of improving those technologies with time and bringing down the prices. So this model is coded as an object-oriented program in MATLAB. We have 250,000 laborers or consumers. You can think of these as households. 200 consumer good firms, 50 capital good firms. 3 energy technology firms associated with each of these technologies, and 1 energy production, 3 producing each of these technologies, and 1 energy production firm, a kind of utility. You could think of it as a monopoly utility. The model is currently calibrated to match US historical trends. That means to match a historic GDP growth rate of 1.7% per year and residential energy use growth rate of 0.7%. Now keep in mind, these aren't exogenous to the model. They're not specified themselves. The stochastic innovation processes are calibrated to lead to these. In other words, we have micro-level assumptions, and these are the macro-level trends coming out of the model. So using the model for simulation, the model works, it does its thing in this program, and consumer good firms are producing the needs and selling them to laborers and consumers, and capital good firms are producing machines, energy technology firm is producing energy technology, and energy is being produced. We can track variables over time, like labor productivity, which is expected to grow through this innovation process, GDP over time, which is noisy but also expected to grow, energy intensity, which historically has declined and which we might expect to continue to decline because of technology development. Energy use is especially noisy, associated with economic trends and other things, but declines in part because of declines in energy intensity. And then CO2 emissions are generated by the model. And these, again, are noisy and are largely associated with energy use. But interestingly, as renewable energy comes online, then CO2 emissions drop, as we might expect. And so under this particular simulation, we see a penetration of renewable energy by the year 2080. Now, random sampling of uncertain inputs is used to generate a variety of different possible outcomes. Because we're not sure about the particular parameter specifications, we want to explore this parameter space. And so in reality, we run this model hundreds of times and look at the scope of possible results coming out of it. And this range of outcomes indicates the scope of plausible futures. And then the model, once kind of calibrated and tested, can be used to play out different national strategies. For example, we might want to evaluate 4 policies. Let's say a reference policy of no carbon tax, a policy in which we implement a carbon tax and give the revenue back to households, a policy in which the revenue, households to spend as they like, just a way to kind of close the loop on the tax. One in which the revenue is given to capital good firms to support their innovation process however they might like to, and one where it's given to energy technology firms to support R&D in renewable energy technology. So these are the kinds of specific policy choices that in reality we have to make, and yet many models of climate change policy gloss over because they're not able to represent the kind of decision processes at the lower level in the firms and the households. So here's an overview of these results that were accepted and are in press in environmental modeling and software. Basically what we see, these are trends on GDP, energy use, emissions, and energy price. The reference case in black, and what I especially want to point out is that the household rebate and industrial R&D both have a carbon tax, and indeed that brings up energy price and brings down energy use, but it doesn't really make a big difference in the long term. I should be pointing to this plot. It doesn't make a huge difference in the long term regarding emissions. What does make a difference is the policy on carbon-free R&D, because if we're able to develop low carbon technologies, that'll make a more dramatic difference in future carbon emissions than the tax itself. In other words, we conclude carbon tax functions better as a carrot than as a stick, right? In other words, the disincentive associated with paying the tax doesn't have a large impact relative to the incentive provided by the subsidies that could come from the revenue of the carbon tax. And this is shown here. This is showing, as a function of year, the carbon intensity relative to our reference case of each of these different policies. What we see is that there's only relatively low decline in the household rebate scenario as a result of the carbon tax. This is a kind of reference for the carbon tax scenario. There's a greater decline in industrial R&D and an even greater decline in carbon-free R&D, meaning the difference between these policies is largely a matter of how the revenue is spent rather than the existence of the carbon tax itself. As I say, model stochasticity and random inputs lead to a diversity of possible outcomes for any one strategy. So we might be interested in, we are interested in exploring what particular socioeconomic and technological developments lead to desirable versus undesirable outcomes. I didn't point it out in the last slide, but any one of these has a broad diversity as a result of uncertain model inputs. And so which particular configuration of parameters leads to stellar success, this is GDP, large improvements in GDP as a result of kind of unhinging energy use from carbon and from rising fuel costs, versus policy failure, meaning something that's not much better than doing nothing at all. Is it energy efficiency improvements, labor productivity changes, technology innovation, energy technology experience? Which one is it that drives this? I'm going to, in the interest of time, I'm going to skip over this slide. This is a kind of motivation that IPCC has indicated the need for this kind of scenario development, evaluating socioeconomic improvements and developments that might lead to different possible outcomes. And we think our model can contribute to that. In fact, we developed a statistical technique described in another paper in environmental modeling and software called multidimensional scenario discovery. It takes a recognition that each simulation is a trajectory in multidimensional space. You could think of it as a kind of bundle. This is a cable. You could think of it as a kind of bundle of simulations that might behave. Each simulation is a point in space, and the cluster analysis identifies these bundles, meaning groups of simulations that have similar trajectories with respect to their main outcomes. This is a slice of that bundle regarding two of the key outcomes of the model: annual consumption, a measure of economic well-being, and annual emissions, that is the kind of potential for climate damage. And the cluster analysis identifies these bundles in this space, in this case, 5 distinct bundles. I'm showing box plots here of these same variables just to identify that there's diversity among these bundles with respect to these two variables. I won't go through this in detail in the interest of time, but what we pull out of this is then, these are the same 2 box plots. What we pull out of this is identifying within these bundles which of these variables is much more strongly discriminated. Because of those, then, we can associate with being the primary correlates with these outcome variables. And when we look at combinations of these, we can then generate a kind of narrative. So if we look at these 3, for example, we see that all 3 of these have similar levels of carbon-free innovation, but they're different with respect to their labor productivity growth and their need energy efficiency, which leads to then different outcomes with regard to emissions and consumption. And so we can give kind of titles to these and storylines which policymakers can understand. And it's intended that these scenarios span the scope of possible futures in an understandable and understandable narrative way that's consistent with model building assumptions. So a kind of summary on agent-based modeling. These agent-based models can be used to test the effectiveness of a variety of strategies, and the multidimensional scenario discovery identifies consistent relationships among the many possible simulations in social, technological, and economic variables. And that's an important innovation in using agent-based modeling, to then use the results in a way that then generates possible scenarios for use by this model as well as other models. And that was the motivation of the IPCC, the Intergovernmental Panel on Climate Change. And so we hope that this can contribute to that effort. I'll take the last minute or two just to give you a little bit of outlook of where we're headed. What we'd like to do with this agent-based model is add some capability in a few key areas. We want to encode uncertain fuel price growth, greater diversity in household preferences, and uncertain population growth, none of which is currently accounted for in the version of the model I described. We want to also allow the model to enable the model to consider endogenous policies. What I described were exogenous policies, meaning a specific a carbon tax that we specify and use to run the model. We might also imagine a situation we could, for policy exploration, in which a carbon tax is responsive to emissions levels. So there's a kind of feedback between those two. And so we're working to be able to do that with the model. And then implement a voting mechanism to tally up individual agents' preferences for different climate policies as a kind of representation of a democratic policy regulation process. And that has links to our second objective moving forward, to link this agent-based model with a game theoretic model that's being developed by one of my students, Peng Ding, of international climate negotiation. And in this model, negotiators are modeled to engage in a two-level game, meaning that they're engaged in treaty formulation with other nations, and this is simulated with a heuristic negotiation algorithm, but at the same time have to satisfy the interests of their constituents. And this is this two-level interaction that we hope to explore by the combination of an agent-based model and a game theoretic negotiation model. And we're interested in addressing the question, what particular negotiation structures and treaty types enable or constrain agreement among parties at both the national and international levels? But this effort and the one I just described are specific aims of a National Science Foundation grant that we're currently working on. And so we're committed to following through on those. The next one is, has been part of a proposal that we recently submitted. And we hope to use the model, we plan to use the model to evaluate the potential of sector-specific initiatives to serve as a kind of bridge between the current situation and potential future carbon taxes. These kinds of initiatives that are sector-specific could yield private benefits to individual actors, meaning they could be in their own interests, and that may spur technological change, which then could spread to broader sectors and other regions. And so we want to address the question, what key features of sectors and policies are most likely to achieve success in this kind of environment by catalyzing the development and adoption of low carbon technology. So I want to thank you for your attention. You certainly deserve another cookie if Joe will let you take another one for allowing me to go a little bit over time. I want to thank the members of my research group, particularly those that contributed to the research I described today, including Research Assistant Professor Michael Gerst, graduate student, PhD student Peng Ding, who I'd like to point out, we just found out this week, has a job offer to work with the Bank of China under the auspices of the Vice President on Strategy and Development. So I guess we could all expect to work for him someday. Peng was involved in doing, in the hierarchical Bayesian modeling, doing the kind of heavy coding behind the Markov chain Monte Carlo approach that was necessary there. Peng Wang was responsible for the coding of the object-oriented program of the agent-based model. And Adam Bernstein, who's a master's student and a graduate of Tuck, advised us on some of the financial data and helped to assemble and understand those data. This work was also performed in collaboration with a number of other colleagues, especially Professor Rich Howarth from Environmental Studies, who's here today, and was a key player in most of the work that I described today. This was undertaken collaboratively. Also, collaborators in Italy who developed the initial economic foundation for the agent-based model I described, and Guri Bong at the Center for International Climate and Environmental Research in Oslo, who's a political scientist who's working with us on the negotiation parts. And the work I described today was funded by the EPA STAR grant and a National Science Foundation Decision Risk and Management Sciences grant. And other work in our group is funded by the National Institute of Health and the National Institute of Environmental Health Sciences. So thanks for your attention, and if I can take a question or two, I'd be happy to. Yeah, Elsa.
I'm embarrassed by asking a question about something you talked about. Present value utility, what does that mean?
It simply means that we take our returns or our variable in its natural metric, cookies or consumption, plug them into the utility function, so we get a utility, and then for utilities that occur far out in the future, we discount them back to the present value using a discount rate.
So what is a utility?
A utility is a measure of well-being characterized by this function, capturing the aspects of diminishing marginal satisfaction with cookies and also capturing the aspects of risk aversion. So it's this function I showed early on that is intended to describe our well-being, where the output of the function is a measure of our personal satisfaction. Thanks for that question. I'm sorry I didn't make that clear. Yes, Alex?
Your system makes it impossible to account for policies that would be imposed against the general will of the population, but which would be known to be one of the better solutions to a given problem. And I'm thinking, for example, public transportation as opposed to individual cars.
Sure. Does it? Well, the first model I described, the kind of decision theoretic one, doesn't. In fact, it's trying to identify what's in the public best interest despite their own behavior. I mean, more or less. Given the kinds of preferences that the public seem to be revealing, particularly through their investment behavior. The agent-based model, you're right. If there's not an incentive structure whereby people should take buses, then they wouldn't do it in our model. So it's intended, that agent-based model is intended to be a little bit more descriptive, to say if we try to impose a policy, what's likely to be the result? Yeah, good point. Yes?
I have a question about age. Most decision makers are old, and it seems they're not going to live past 20, 30, 40, 50. Few here are going to live to 2100. And if a survey was made with concern about climate change versus your age,
Yeah.
I'd be fascinated with how it came out.
I'd encourage you maybe over another cookie afterwards or a cup of coffee to talk to the guy in front of you here, Rich Howarth. He's particularly interested in aspects of intergenerational equity and intergenerational concerns. That's not something that I'm dealing with here. It's a complicated issue, but that's something that I think he'd be happy to engage you on.
Older people tend to be more altruistic than people who are middle-aged.
They tend to be more risk averse.
Altruistic.
Altruistic, I see.
Care about their grandkids.
Okay. Right, and that issue, the fact that kind of in our model we're assuming we live forever and that these are our preferences expressed in that way, the aspect of discrete generations that are overlapping raises another set of issues, and maybe you two could engage in it after. Yeah. Yes?
I just noticed that in the graph where you have the red line and the blue line, and the blue line is abatement or amelioration, and the red line is rising emissions and destruction and stuff like that.
Yeah.
All of them end up with an upward curve at the end, which seems to sort of indicate that there's an inevitable, the curve
Yeah.
is just being postponed no matter how good your scenarios are.
You're absolutely right. Yep, it's because of the residence time of carbon in the atmosphere. I mean, no matter how significantly we reduce carbon now, we're kind of stuck with a certain amount of climate change. And that's what that's reflecting. Yep. Yes? Oh, yeah, here.
So you have an agent-based model. There must clearly be an agent that's whose best interest is served by not having carbon tax,
Yeah.
and not having
Yeah. Yeah.
renewable energy. And they tend to influence the decision makers by way of campaign contributions and other kinds of things. There's a function there you could model,
Yeah.
which would show if you break that function, you might get better outcomes.
Great point. And I had to go through this a little bit quickly. I simplified this as a voting mechanism. It's actually a voting and lobbying mechanism. No, I mean, we'll intend to account for special interests and their own self-interest. That's one of the next steps. Great point. Thanks for raising it. Yeah, hi, Lee. Yeah. Lee?
Yeah, so two-part question. First of all, just briefly trace out, I can imagine, but I'm interested to hear what you say. Trace out the path from this research to the hoped-for world impact, just so.
Yeah. Thanks. Yeah, again, based on my timing, I didn't elaborate on some of these as much as possible. The hope is, with the model is twofold. One, to perhaps improve the negotiation structures at an international level, provide some insight into ways to improve that. This is with the two-level model I described, by recognizing that government representatives at the international negotiations are in the tough position of both having to participate in a negotiation but satisfy the interests back home. And so the goal of the larger grant that incorporates both of these is to say, how do we do that? What kinds of mechanisms, both at the treaty negotiation level and at the domestic implementation level, are mutually compatible? So we hope to shed some light on that. The other point is to help appreciate the risk reduction value of climate change mitigation, to say uncertainty shouldn't be a cause for policy paralysis. But in fact, the more uncertainty we have, the greater the risk and the more need we have to take some action sooner rather than later. So it provides an additional argument for climate change. And then once some policy were to be being explored, the agent-based model would be an opportunity to play that out and see how successful it might be relative to its alternatives, given some of the key real-world constraints.
Additional argument for climate change or climate change mitigation?
I'm sorry, thanks. Argument against climate change, for climate change mitigation. Thank you. I need one of those cookies. I don't know what kind of timing. I don't want to keep everybody. One more question? Gwen?
Yeah, so I had a question about, you showed us some graphs where there's sort of trajectories that are tied to different policies with the agent-based model. And I was wondering if you thought explicitly about how coalitions of these policies might do, because like my intuition is that sometimes the feedback could be synergistic in some way that gives you super linear effects, and maybe you're having a way to measure these synergistic effects that says two policies that cost A and B together have benefits way greater than we anticipate from the cost of A and B.
Yeah, no, that's a super question. We've put so much time and effort into developing the model and testing just the most basic scenarios. We haven't gotten there yet. But that is, I mentioned the NSF proposal that we had submitted recently, looking at bridge policies. It also looks at what we call hybrid policies, combinations of what might be second best policies, but which could, in the end, be more successful than what we might consider to be an optimal policy because of those kinds of synergies. It's great. Yeah, that's absolutely right. All right, I should probably excuse.
Those of you who have more questions, the corner Mark before he goes. Thank you, Mark.
Great, thanks. Hi, David. How are you? Thanks for coming. Yeah, I appreciate you making it.